In this video, we're going to take a look at approximating areas under curves. So in the past, we've looked at derivatives and how derivatives of a function, if we go down this path here, derivative tells us a slope of a tangent line or an instantaneous rate of change. So that's one of the implications of a derivative, and then there were several applications after that. Well, now we have this technique of anti-differentiation or integration, and so our question is, what does this tell us? So to answer that, let's take a look at a velocity function. Let's just take a plain, ordinary velocity function where we are moving at a velocity of 60 miles per hour and we're constant. So we want to ask, all right, well, if we're moving 60 miles per hour, in 2 hours, how far do we go? So if we look at 2 hours is the time, 60 miles per hour is our velocity. We know, well, to find our distance, that's just equal to the velocity times the time. So that's 60 miles per hour times the 2 hours, and that gives us 120 miles. Okay, so another way we can look at this, let's look at the graph of a velocity versus time, and let's draw the rectangle. Okay, pretty terrible rectangle, but you get the point. So let's draw the rectangle at t equals 2. So if we look at the area of this rectangle, well, what do we get? Well, the height is 60 and the width is 2. And if we want to even do units, this is miles per hour, and these units are hours. The area, we multiply those together to get an area of 120 miles. So the area gives us this product of the x component and the y component, or the independent variable and the dependent variable. Just like the derivative gave us a slope or a ratio of the rate of change of the vertical component to the horizontal component, this gives us a product. Finding the area gives us a product of our two axes. And so we see here that the product of that area gives us 120 miles. Now what if we have a different curve, like v equals t squared? So now our velocity is changing as time goes on. Well, we could try to find that same area under the curve, knowing that the area is going to equal the displacement, okay? Because that's how far we're going to move, because that area tells us the product of v times t. Well, how are we going to get the area under this curve? It's not a nice shape. If we want to go from, say, 0 to 8, we don't get a nice shape. Well, we have an option here. We can break it up into rectangles. We could say it's really two rectangles. We have a rectangle here from 0 to 4, and we have a rectangle from 4 to 8. Now, you might say, now, wait a minute, that's a pretty terrible approximation because we have all of this area that we're not counting, or this area that we're not counting, and we are counting this area, but we shouldn't, and we are counting this area but we shouldn't. And so yes, this is a crude approximation, but let's say that's only with 2 rectangles. Let's say we do it with 4 rectangles, and we break it up into a subinterval. Instead of a width of 4, now a rectangle has a width of 2, and we add up the area of each of these rectangles. Well, we still have some air in our area, but now that air is a little less. And you can see where this is going. If we break it into 8 subintervals, that air gets even less still. And then if we break it up into 64 subintervals, that looks like we're pretty darn close to the actual area. Yes, we do have a little bit of air, little overshot there, and a tiny little undershot in these corners here, but it's very tough to see. So what we're getting at here is we can approximate area under a curve by breaking it up into a series of rectangles and adding all the areas of those rectangles together. And so if we did that, and so here's some calculations with it, looking at just one rectangle, one subinterval, we get an area of 128 meters. But if we do 2 subintervals, well, we get 160, and then so on and so forth. If we do 64, we get close to 170, almost 171. And look at the values here, how they get closer and closer and closer. And so the limit is approximating what we believe to be the true area under that curve. So in order to look at any curve, say we have y equals some f of x, some function, and we want to look at the region from A to B, the area under that curve can be found by using this technique breaking up into these tiny little rectangles and approximating the area. Now, in order to do that, we need to be able to break up into subintervals. And so we need to know what is our delta x. And so if we're starting at some value a, our initial x value, which we're going to call x naught or x sub 0, is going to equal a. And our final x value is going to equal b. And so that's going to be some x sub n being the number of intervals we have. This is the number of intervals that we're going to break our area up into. And so to find each subsequent x, whether it's x1 or x2 or x3 or x so on and so forth, all we have to do is just look at it's just delta x is our difference in between, and that delta x is constant, and it's the same for all the spaces in between x2 and x3, in between x15 and x16. And so we get these subintervals as listed here, x0 to x1, x1 to x2, all the way up to xn minus 1 to x sub n, where once again n is our number of subintervals. And we can look at our delta x is going to be equivalent to our interval width divided by the number of subintervals. So we have b minus a over n. So like the example before, when we wanted to go from x is defined from 0 to 8, and we wanted to do that in two subintervals, well, we looked at 8 divided by 2, so that gave us a delta x of 4. Okay, well, if we wanted to go 16 subintervals, we would have a delta x of 1/2. And so that means that the space in between each of these would be 1/2 all the way up until we get an x sub 16. And so that gives us those 16 subintervals. And so a little formula that we're going to use here, and it might look confusing at first, but it does make sense for us in that x sub k is equal to our starting point plus k times delta x. What is k? K is the index. So if we want to find x sub 15, we just take 15 times delta x and add it to our starting point. So we break up our area into as many subintervals as we want, and then we're going to evaluate at some x value that's in between x0 and x1, and some x value that's in between x1 and x2. Now what we're going to do is we're going to actually systematically do this and find that we can use these approximations to give us some more information. But basically the area of this rectangle is going to be f evaluated at some value in between our subinterval times delta x. And then if we add all of those rectangles together, that would give us an approximation for the area under the curve. So in order to do this, we do what's called Riemann sums. Now Riemann was a mathematician that came up with this technique. And he came up with a way to approximate area with a left-handed sum, a right-handed sum, and a midpoint sum. And they all have their own advantages. So in a left Riemann sum, we use all the left endpoints. And we'll see what we mean by this in a moment with an example. With the right Riemann sum, we use all the right endpoints. You know, that's why it's called left and right. With the midpoint Riemann sum, we use a midpoint between our endpoints in each subinterval. So we actually don't use any of our interval endpoints. We use a number that's halfway in between our intervals to evaluate in our function. So to get a picture of this, looking at this curve, the left Riemann sum, notice how the left end of the rectangle is in contact with the function. So we're using that point to define the height of our rectangle. The left point defines the height of our rectangle, whereas in a right Riemann sum, the right point defines the height of our rectangle. So just flipping back and forth between these, we see that there's a slight difference in the air. All right, and we'll talk about which one's an overestimate, which one's an underestimate, and why and when later, but we see that they each have their differences. And a midpoint, we kind of go middle of the road there, and we look at the midpoint in between these are going to give us the height of our function. Let's look at an example here. Let's say we have a function f of x is equal to sine of x. And we're going to look on the interval from x equals 0 to pi, and we want to do a left approximation with 4 subintervals. So that's what this means. L sub 4 means left approximation of 4 subintervals. So that means our delta x is going to equal b minus a over n. So delta x is equal to pi over 4. So looking at the graph, if we look at sine here, we see that we cross at pi, but we're going to break this up into 4 subintervals. So we split it in half and then split it in half again. So those are our 4 subintervals. We've got pi over 4, pi over 2, 3 pi over 4. So let's actually write down our x values. x0, x1, x2, x3, and x4. And this chart is very helpful, especially when you're starting to do these. So we start at our a value, which is 0, and then we add delta x each time. So we get pi over 4, add another pi over 4, we get 2 pi over 4, which is pi over 2, add another pi over 4, that's 3 pi over 4, and then add another pi over 4, and that gives us pi. So for a left approximation, we are going to use the left 4 points. So our left sub 4 is going to equal our delta x times f evaluated at x0 plus f evaluated at x1 plus f evaluated at x2 plus f evaluated at x3. And so we notice these are all 4 of the heights of our rectangles that we're going to draw here. Here's the first one, here's the second one, here's the third one here, the third rectangle, and then here's the fourth rectangle. Okay, so we notice we're definitely pretty low. We're losing some area there, but we have a little overestimate there and a little overestimate there to hopefully make up for it. So if we plug these in, we can evaluate L4 is going to equal pi over 4 times our function evaluated at x0. Well, sine of 0 is 0. And then sine of our pi over 4 is radical 2 over 2. Plus sine of pi over 2, that's 1. Plus sine of 3 pi over 4, that gives us another radical 2 over 2. So we can add these together. We could distribute the pi over 4 together either way. But if we add these together, we end up getting a pi over 4 times the quantity 1 plus radical 2. And so this is our approximate area underneath that curve. Now, we could do a right approximation as well and do a right sub 4, and it would be very similar, except the difference, we wouldn't have the f sub 0. We would start at f of x1 and then go up to f of x sub 4. And then we'd multiply that whole result by the delta x. And so that right approximation could give us something a little different. Actually, you'll find the symmetry in sine is that you get the same value, which is kind of cool. But either way, we can get the right approximation by doing the same thing, but using these right 4 values instead of the left 4 values to define the top. Now, if we were to do a midpoint approximation, the midpoint would be a little different. Now we have to evaluate at the midpoint of each of these, and so the midpoint at each of these is actually going to be a new value altogether. Instead of pi, the midpoint between 0 and pi over 4 is pi over 8, and the midpoint between pi over 4 and pi over 2 is 3 pi over 8, and so on. And so those would actually be kind of nasty numbers and wouldn't be fun to evaluate, but we could do it. And so the midpoint approximation could be done using those values there. We are going to continue to use these in class, as well as look at what happens when we say n is equal to some really number like 50 or 100, and how do we actually do that without doing the individual computation. So we'll continue to expand on this in class.